The second colligative property is known as boiling point elevation. Now, sort of like it sounds, boiling point elevation is simply stated as the presence of a non-volatile solute particles increases the boiling point of a liquid. So if we take pure water and think about its boiling point as 100 degrees Celsius, if you take that water and dissolve sodium chloride into it, the boiling point of the new salt solution is now greater than 100 degrees Celsius, and we can quantify that. But before we quantify that, let's just look at why the presence of solute particles increases the boiling point. This is actually related to the last colligative property, the vapor pressure lowering, because here in black is shown the normal phase diagram for the solvent. However, remember that when we dissolve solute particles into that solvent, the vapor pressure lowers. And so if we look at this black line here as being the vapor pressure of the pure solvent, the vapor pressure for the solution is lower than that. And so the blue line here is now showing the new vapor pressure curve that is at low, that starts at a lower value because of the decrease in the vapor pressure due to dissolving solute into the solvent. What results from that then is that, remember that the boiling point is the point at which the vapor pressure is equal to the atmospheric pressure. So if we follow our curve along, what we will notice is that we hit that point where the vapor pressure equals the atmospheric pressure at a higher temperature value than we would in the black curve, which is for the pure solvent. Now, this difference here is essentially the amount of elevation of that boiling point. So we are at a higher boiling point in the solution than we are for the pure solvent. Now, we can nicely correlate this change in boiling point quantitatively. So we can correlate the change in boiling point temperature to the solution concentration. That's little m here in molality. So this expression here, delta TB, is simply the boiling point for the solution minus the boiling point of the pure solvent. I is known as the Bant Hof factor, and this is simply the number of solute particles. So if we were thinking back to our example when we were doing vapor pressure lowering, when we were doing lactose, I would have just been 1, whereas sodium chloride was 2. Sodium chloride breaks into the sodium ion and the chloride ion, so we get 2 ions for every 1 molecule of sodium chloride, so I is 2. And by extension, that's how we use the Bant Hof factor when we're looking at the identity of the solute. Kb here is known as the molal boiling point elevation constant. It's not exactly very concise, but there are tables of values of these. And then M is the molality. So this is moles of solute per kilogram of solvent. And we can again remember why we might use molality here rather than molarity, because molarity changes with temperature, which is exactly what we are looking at, but molality is independent of temperature. And so that's why molality is really preferred in this case, or necessary even. So how might we use this to calculate the change or even just the new boiling point for a solution? Well, here's an example. So calculate the boiling point of a solution that contains 50.50 grams of sodium chloride in 200 grams of water at 25 degrees Celsius. And we're given the molal boiling point elevation constant. We're given the molar mass of sodium chloride. So what we are really looking for, we are looking for TB of solution. We know TB of the pure solvent, it's water, so it's 100 degrees Celsius. I depends on the solute, in this case it's sodium chloride, so I must be 2. And we're given Kb, and we can figure out M as moles of solute over kilograms of solvent. We can figure that out from the values that are given. So let's work our way through this. So I is 2, dependent on the sodium chloride. The 50.50 grams of sodium chloride, we can convert to moles. So that's moles of solute, 0.8647 moles of sodium chloride. And then we take the molality as simply being the moles of sodium chloride divided by the kilograms of water. and we'll come out with 4.324 molal in this case. Now, all we need to do is essentially plug into our equation and rearrange. So first, we plug in and find what delta TB is. This is the change in temperature. Substitute 2 in for I, 0.51 for K, 4.324 for M. We come up with a change in temperature of 4.4 degrees Celsius. Now, this isn't what we've been asked for, though. We haven't been asked for the change in temperature. We've been asked for the actual new boiling point. So if I take that delta TB is equal to TB of the solution minus TB of the pure solvent, I can simply rearrange that equation to have TB of solution is equal to delta TB plus TB of the pure solvent. So that's 4.4 plus 100.0, and I come out with 104.4 degrees Celsius as the boiling point of this new solution. Now, just like boiling point elevation, we also have an impact on the freezing point by having dissolved solute. And this is opposite to the boiling point. In this case, the presence of solute particles decreases the freezing point of a liquid. So again, we can look at our vapor pressure curve that we've done before. And what we saw is that when we lower the vapor pressure, what happens is that we intersect the solid line at a lower temperature than we would for the pure solvent. So my triple point occurs at a lower temperature value than it does for the case where we have pure solvent. As a result, I have a delta TF here, which is the change in temperature for the freezing point. And very, very similar to the boiling point elevation, I can relate that quantitatively to the concentration of the solution using this equation here, which is almost identical to the boiling point elevation equation. It's simply delta TF is equal to minus I, which is again the Bant Hof factor, KF times M. So what are all of these? So delta TF is again just the change in the freezing point. So it's temperature of the solution, the freezing point of the solution, minus the freezing point of the pure solvent. I is the Bant Hof factor. KF is now the molal freezing point depression constant, which will be given to us in a table. It's different from the molal boiling point elevation constant. And then M is still molality. So we can do another expression here, calculate the freezing point of a solution that contains 50.5 grams of sodium chloride and 200 grams of water. This is exactly the same as the last problem. It's just that we're looking for the freezing point, not the boiling point. And we're given KF as now the molal freezing point depression constant as 1.86 degrees Celsius per molal. So the same process exists. I is 2. We convert sodium chloride to moles. That's moles of solute. Here we take M and determine the molality by dividing the moles by the kilograms of water. It's the same value, 4.324 molal. And then we determine the change in temperature for the freezing point. This is delta TF as being negative 16.1 degrees Celsius. So with this value in mind, we're asked for the freezing point. So just like the last time, we need to rearrange the delta TF equation to solve for the TF of solution. That's delta TF plus TF of solution. So negative 16.1 plus 0 gives us a freezing point now of negative 16.1 degrees Celsius. So this is where this is how we use expressions to quantitatively talk about these two colligative properties, freezing point depression and boiling point elevation.